We're starting a new unit now called counting. As you can see by the lessons here, the lesson names that are listed here, we're not just talking about counting as we would be, in kindergarten, that kind of counting. What we're doing instead is learning how to count the number of ways different things can happen. Over here on the right, I've just put a sample of the different types of questions that you're going to be learning how to answer here in this unit. You can take a look at that. You'll see all of these again throughout the lecture, and these are just some. There's a lot more that we're going to cover, but it kind of shows you the different types of things that we're going to be learning how to do. And probably the biggest challenge for this unit won't necessarily be understanding each lesson separately, but it will be when it comes time for the test, when you're given questions like you see over here on the right. Your challenge will be knowing what type of question it is, how which of, if you read a question, which lesson over here on the left did we do we need to use in order to answer the question, because there's different categories of these different questions. And so that will be your challenge, is to be able to read a question and know, oh, this one is one where I need to do counting by complement, or maybe, oh, I'm counting multi-sets in this problem, that kind of thing. But don't worry, as we go through the unit, as we learn more and more categories, you'll eventually see how everything does fall into place, fall into its own category. And what I do for you to study for the test, this next test that we have will just be over just this unit on counting. And so it will just be made up of just a bunch of questions like what you see over on the right. What I will do is give you a study guide where you'll have a bunch of questions like this, and you'll get some practice in being able to look at a question and know which category it falls in, so that you'll know how to answer the question. So you'll get some good practice with that. So don't worry, try to just focus on each lesson each time, so that you understand how to do that particular problem, and then know that you're going to be getting some good practice towards the end, so that you'll be able to distinguish between the different types of problems when it comes to answering these problems on the test. Now, the first two sections in this unit involve the sum and product rules and the generalized product rule. Now, even though the book puts them in a certain order and has it in two sections, I would like to present it in a little bit different order as the book does. So I'm going to lump both of these two sections together and talk about them all together, because I will be talking about things that they would put in that second section, maybe before I talk about some other things that are in the first section. So we'll just lump it all together, and first of all talk about these two sections together, covering the sum and product rules and the generalized product rule. So before we look at this product rule that's up here in the box, I want to point out some notation here. We're going to be talking about sets. You see, it says let A sub 1 up through A sub n be finite sets. But let's talk about on that last line, you see some X's there. Looks kind of like time symbols. And if you remember from what you've learned about sets, is that symbol, when you have sets on each side of that, means that we're talking about the cross product. Okay, so that so when we see A sub 1 with the X and A sub 2 and so on, we're taking the cross product of all of those sets. But now, besides that cross product there on that bottom line, you also see the straight up and down lines. And remember what that is when you have that on the outside of what would be a function, a set inside, means how many elements are in that set. So on the left side of the equal sign, we're saying how many elements are in this cross product. That's what's on the left-hand side. And then on the right-hand side, we see that we're being told that that's equal to, and then we have a sub 1 with those symbols. So we're saying the number of elements in a sub 1 times the number of elements in a sub 2, and so on, up to times the number of elements in the last set. So let's now read this. It says, let a sub 1, a sub 2, up to a sub n be finite sets. Then the number of elements in the cross product of all of those is equal to the same thing as if we were to take the number of elements in A, multiply that by the number of elements in, a sub 1, multiply that by the number of elements in A sub 2, and so on. So just multiplying all the number of elements in all of those sets, multiplying them together. Now at this point, I know it probably isn't making a lot of sense, so let's look at an example. Let's talk about rolling 2 dice. If we take 2 dice and we roll them, we can take a look at this chart and see that there are these different possibilities here. So over on the left, I have die 1. That could go from 1 up to 6, right? You could get either a 1 up to a 6 for the first, on the first die. On the second die, again, you could get from 1 up to 6, and so we have those numbers across the top. So we might consider what we would get for die 1 as one of our sets, and the elements are 1 up through 6. So there's 6 elements in our first set, and then in our second set would be the number that we would get, possible numbers that we could get when we roll the second die, and that would also be 1 through 6. So what you see inside this table then would represent the cross product. It's this ordered pairs that we would get. So you see at the very top left, we could get a 1 for both die 1 and die 2. So that could be represented by the ordered pair 1, 1. Right below it, this is the ordered pair 2, 1. That would represent the fact that we would get a 2 from the result of rolling die 1, but we'd get a 1 when we roll die 2. So anyway, you see all of these different possibilities here, and so all of these ordered pairs would be elements in the cross product of the 2 sets. So a sub 1, we would say again, would be just the set of 1 up through 6. And that could be, again, represented by the possible values for die 1, okay? And how many elements are in there? We would say there are 6. We could say a sub 2 then are the possible numbers that we would get when rolling die 2, again, 1 up through 6, and there's 6 elements, so the magnitude of a sub 2 would also be 6 because there's 6 elements in there. Now, let's use the product rule. The product rule says that the number of elements in the cross section, or the cross product of these 2 sets should equal the product of the number of magnitudes in the 2 sets. So let's check. The cross product a sub 1 and a sub 2, the cross product of those. The product rule says that it should equal this, the product of the 2 magnitudes of the 2 sets, and that would give us 6 times 6 and 36. And if we can look over here on the left and look at that table, and we could count, and we see, yeah, sure enough, there are 36. So this is just an example of the product rule. There were 36 elements in the cross product of A sub 1, and A sub 2. And we could have found that by using the product rule, or we could find it as we did here by listing out all of the different possibilities. Now here's a type of question that we can answer using the product rule. The question is, how many strings of zeros and ones of length 4 are possible? You see that I've marked off 4 positions because the string needs to be of length 4, and I have an example in here where I have the number 1001. But, we could also have other strings. There's all kinds of possibilities there where we would have different combinations of zeros and ones. So we want to see how we could use this product rule to answer this question. So let's think about it this way. Think about the possible elements that would go that could possibly go on in this first slot. We could call that A sub 1, and we know that since this is just a string of zeros and ones, we would have only 2 possibilities, zeros and ones. So we could say that A sub 1 is a set that has only 2 elements, 0 and 1. Then let's say A sub 2 is looks the same. It has 2 elements, 0 and 1. Same thing with A sub 3 and A sub 4. Now, looking at the number of strings we could see that could just be looked at as the cross product of all of these sets. So let's take the cross product of A sub 1 and A sub 2, A sub 3, and A sub 4. Well, if we don't really care right here what all of the elements are, because the question was how many are there. So we'll just take a look at, we're just going to be trying to find the number of elements in that cross product, and so we could use that product rule that says the number of elements in that cross product is equal to the product of the magnitudes of each of those sums. So A sub 1 would have 2 elements, and then A sub 2 has 2, and so on. So it would just be a matter of multiplying 2 together 4 times there. And so we would have 16. And so we could say that we've used the product rule and been able to determine the number of strings of zeros and ones of length 4 would be 16. Now, there's what's called the generalized product rule, which is kind of a little bit easier to understand than thinking about these cross products. And so from here on out, really, well, we'll just talk about this product rule in terms of this using what's called the generalized product rule. Here's what the generalized product rule says. It says, in a sequence of k events in which the first event has n sub 1 possibilities, and the second event has n sub 2 possibilities, and the third has n sub 3, and so on, the total number of possibilities of the sequence will be n sub 1 times n sub 2 times n sub 3 all the way up to n sub k. So this same problem that we just looked at, we had the question, how many strings of zeros and ones of length 4 are possible? We can look at that as a sequence of choices. And so the generalized product rule starts out in a sequence of k events. So our events are going to be choices here, and we're going to say, okay, I'm going to be making 4 choices. First of all, I'll make the choice of what to put in that first slot. And how many choices do I have? How many possibilities? I would have 2 possibilities here, either a 0 or a 1 could go there. So that would represent my n sub 1. Then I would go on to my next choice, which would be how many, what would I put in that second slot, and how many possibilities are there? Again, 2 choices, and 2 choices for the third slot, and 2 choices for the fourth slot. So this generalized product rule says that the total number of possibilities for this situation here would be multiplying all of those numbers of choices together. So we would have 2 times 2 times 2 times 2 would give us 16. So we've solved the same problem. We've still used the product rule, but we're seeing it in terms of, instead of looking at this cross product, we're just seeing it in terms of, let's make a choice for the first slot, let's make a choice for the second slot, and so on. And then let's look and see how many choices do we have for each of those decisions, and then we'll multiply all of those together, and that's how many possibilities we would have. Here's another example where we could use the generalized product rule. A paint manufacturer wishes to manufacture several different paints. The categories include the following. We've got different colors, so we're just going to just have some basic colors: red, blue, white, black, green, brown, and yellow. We're not going to say we are mixing them at all. We're going to say these are just these 7 colors here are the possibilities for the colors. Then for the type, it could be latex, which would be water-based, or oil-based. Okay, so latex or oil. Now for the finish, it could be a flat finish or a semi-gloss or a high gloss. Those are the options that this paint manufacturer is going to offer. And then for the uses, indoor or outdoor. Now this maybe isn't a good example because there's a lot of paints that say that they could be used indoors or outdoors. And anything that could be used outdoors, there's no reason why we couldn't use them indoor, right? So I guess we probably shouldn't have. I mean, if you're thinking of real life, you would say no. There's not just indoor paint or outdoor paint. Sometimes there's something called indoor-outdoor. You could use it either one. But for the sake of this example, let's pretend that they're going to have just 2 categories, that some of the paint will be labeled indoors, and that will be the type of paint that can't withstand the elements very well. And then they'll also have another category called outdoor paint, and that could be used outdoors and will stand up to the weather. Okay, so we'd have 2 different types of those uses. Then the question is, how many different types of paint can be made if a person can select 1 color, 1 type, 1 finish, and 1 use? So we could see this as a sequence of choices. We're going to choose what the color is, choose the type, choose the finish, choose the use. And so this generalized product rule would say, well, we'll find how many possibilities for that first choice, and then how many possibilities for the second choice, and so on, and then multiply all those numbers together. So there's 7 possibilities for color, two possibilities for type, 3 possibilities for finish, and 2 possibilities for use. So we would just take 7 times 2 times 3 times 2 and get 84, and we would be able to say then that there are 84 different kinds of paint that could be manufactured by this paint manufacturer when you take into account all of these different categories. Here's another example. The digits 0, 1, 2, 3, and 4 are to be used in a 4-digit ID card. How many different cards are possible? How many different numbers, it would have to be a different number on each card. So the question is basically, how many different ways can we come up with a 4-digit number just using the digits 0 up through 4? Well, again, we can consider this as 4 choices. What goes in the first slot, what goes in the second, in the third, and the fourth. And so again, we can use that generalized product rule and think to ourselves, how many choices do we have for that first slot? Well, we have 5, right? There's 5 possibilities. 0 up through 4, so that's 5 different possibilities. Then for the second slot, there are 5 possibilities also. And for the third slot, 5 possibilities. And for the fourth slot, 5. So how many different numbers are possible then? We would just take all of these numbers, multiply them all together, and we would get 625. So the answer would be 625. Now, we might have some different requirements here. This is almost the same problem, but it says the digits 0 up through 4 are to be used in a 4-digit ID card. How many different cards are possible if repetitions are not permitted? Meaning in this 4 digits, if I've already have a 1 in there, I can't use another 1. I can't have 2 ones in that digit, in those 4 digits. Okay, that's what it means by repetitions aren't possible. So if I already have used a 3 in the first slot, I can't have a 3 in any of the other slots. So that's what that means. Okay, so this is similar. We can still look at it as a sequence of choices, but we've got to keep something in mind, and that is that repetitions are not permitted. So again, we've got these 4 choices. Let's start again with the first slot. How many possibilities do we have for that first slot? Well, if we consider that first slot as the first choice, then we have 5 choices. We could start with 0 up through 4. So we'd say that there's 5 choices. But now when we get to the second slot, we have to keep in mind that we've already used one of the digits. So whatever we chose for that first slot is no longer a possibility for this second slot. So, we don't know what got chosen for that first slot, but we do know that instead of having 5 choices now, there's only going to be 4 choices, 4 possibilities for numbers to go in that second slot, because we can't put whatever number gets put in the first slot can't be put in that second slot, because we would be repeating, and we can't repeat. So we're down to 4 choices on that second slot. By the time we get to the third slot, we've already used 2 digits. So now we have the original 5 possibilities, but we have to subtract the 2 digits that already would have been chosen. So we would be down to only 3 possibilities. And then for the last one, there would just be 2 possibilities left. Okay, so each time our possibilities go down because we've used up a digit that can't be used again. So now we would look and again use that generalized product rule and say that the number of possibilities then are 5 times 4 times 3 times 2, and we end up with 120. So that would be the answer for that. Here's another example. There are 8 different statistics books, 6 different geometry books, and 3 different trigonometry books. A student must select one book of each type. And let's say that the student gets to decide. Usually, the teacher decides. But let's say in this example here, the student's going to just select a book of each type. How many different ways can this be done? So again, we can look at it as a sequence of choices and say, well, how many possibilities for the statistics books? There's 8 possibilities. And then how many for geometry? There's 6. And then how many trigonometry books? There are 3. So we've got 8 possibilities and 6 possibilities and 3 possibilities. So we would multiply all of that together and get 144. So there would be 144 different ways that these books could be selected. Okay, now this next slide is just going to cover a bunch of problems only using what we've just talked about, this generalized product rule. So let's see if we can do all of these and understand that they're all basically alike. And all we have to do is use that generalized product rule. The first one, how many different 4-letter alphabetical lock combinations are possible if any of the 26 letters can be used, and a letter can be used more than once. So we're saying if we've already used the letter A, we can use it again, so we don't have that restriction. Okay, so again, think about it as it's a 4-letter lock combination. So let's imagine that we have 4 choices again. How many choices do we have for that first letter? Well, there's 26 letters, and we're supposed to just use letters, it says. So we would have 26 choices. For the second letter, well, there's no restrictions on how many times we use a letter, so we haven't used up a letter. So for the second slot, we also still have 26 choices. And by the time we get to the third one, we still have 26, and fourth one 26. So we would just multiply 26 together like that, and we would end up with 456,976 combinations. Now, here's the next question. How many different 4-letter alphabetical lock combinations are possible? If any of the 26 letters can be used, and a letter can only be used once. Okay, so if we use an A, then we can't use it again. Okay, so this is similar to what we just saw. Again, we'd say there's 4 choices here we're going to make, and we'll start with the first letter, and we would have 26 choices. But since a letter can only be used once, by the time we get to the second slot, we only have 25 letters to choose from, because whatever would be chosen for the first slot can no longer be a possibility. So we would be down to 25 possibilities for the second slot. By the time we get to the third slot, we're down 2 possibilities because we've already used up 2 letters. So now we just have 24 choices. And then for the fourth slot, 23 choices. So it's going down by 1 each time. So we multiply all of those together, and we would come up with this number here. Okay, here's another question. How many different 3-digit serial numbers are possible if a number can be used only once? So again, you could think of it as 3 choices, and it doesn't say that we can only use digits 0 through 4 or something like that, right? So we would assume we have all of the digits 0 up through 9 we could use, right? We would have 9 different digits that could go in either of these slots. So 0 is 1 digit that could be a possibility, and then 1 through 9. So there's 10 possibilities. So for the first slot, we would have 10 possibilities. But a number can only be used once. A digit can only be used once. So for the next slot, we would have to go down 1. We would only have 9 possibilities, and for the next slot, only 8 possibilities. Multiply that together, and we get 720. Okay? Now, you know, it's not, sometimes there's even other restrictions. So you might at this point say, okay, it's either going to be the same number multiplied by itself, by itself a bunch of times, or we're going to start with a number and go down by 1. But not necessarily, because there's other, restrictions that we might have. So I would always caution you to just each time look at it fresh, as I've just got these certain choices and I'm going to use the generalized product rule. Because this one says how many different 3-digit serial numbers are possible if the first number cannot be a 0 and a number can be used only once. Okay, so we just have to think it through for each of the digits. So again, it's a 3-digit serial number, so we have 3 different choices. So let's think about how many choices we have for the first slot. It says the first number cannot be a 0. So I would have only those digits 1 through 9 available to me. So I would say that I only have 9 different possibilities for that first slot. Okay, right? Because I couldn't use 0. It said the first number cannot be a 0. So I had 9 possibilities there. Now let's go on to the second slot. The second slot it could be a 0. It doesn't say that it can't. It says only the first number cannot be a 0. So 0 is a possibility. So we throw that back in as a possibility. But a number can only be used once. So first of all, we'd say, well, I could use digits 0 up through 9. That would be 10 possibilities. But I've already used up one of the digits if I'm already on the second slot. So whatever I put in the first slot then can't be used because a number can only be used once in this problem. So in the second slot, it's going to be 9 again, but 9 for a different reason than the first one, right? It's 9 in this slot because it could be anything from 0 up to 9, except that it can't be whatever was chosen for that first slot. So that's why it's a 9. Okay, now let's go on to the third possibility, the third slot. Well, again, for the third slot, there's no restrictions. It could be 0 up through 9, except that we've already used up 2 digits in those first 2 slots. So we'd say there's 10 digits possible, 0 up through 9, but we've already used 2 of the digits up. So it would be 10 minus 2, which would be an 8. Okay, so just have to think through each of those possibilities. And notice here, it's not like the problem above where it started at a 9 and kept going down. We had 2 9s and then an 8. Okay, we multiply those together and get 648. Okay, last problem. How many different 7-digit phone numbers are possible if a number cannot start with a 1 or a 0? Okay, can't start with a 1 or a 0. But it's just that starting number that's the issue. Anything else is fine. So let's think. It's a 7-digit number, so we've got 7 slots to fill. So we'll think, how many different possibilities do we have for that first slot? So we can use all of the digits for that first slot except for 1 or a 0. So that would mean 2 up through 9. So we could count that or just think about it this way. We had 0 up through 9, which were 10 possibilities. But then we have to subtract 2 out because 0 and 1 are 2 possibilities that we can't use. So 10 possibilities minus 2 would give us 8 possibilities for that first one. Okay, so 8 possibilities for that first one. Now, the second one, what would we have for that? Well, once we get to the second one, we don't have that restriction of not being a 0 or a 1. But let's see, how many different ones are possible if a number... Okay, it doesn't say anything about being able to repeat a number. So having used a digit in the first slot is not going to make a difference for the second slot because it didn't say a number can only be used once, right? So by the time we get to the second slot, we've got all of the possibilities open to us, 0 up through 9. So there's 10 possibilities there. And for the third one, 10 possibilities. 10 possibilities for all of these other choices. It was only that first number that had the restriction, and then we could repeat digits because it didn't say we couldn't. So we'll go ahead and know that we can. And so these would be the numbers we would have. Multiply all of those together and we get 8 million numbers. 8 million different phone numbers are possible if the number cannot start with a 1 or a 0. So I think this slide gives you an example of a lot of the different types of problems that you'll have, where either maybe there's no restrictions at all, or there's a restriction having to do with using a letter or a digit more than once, or maybe saying certain slots can only have certain things put in them. And so this is a good representation of the types of problems that you need to be able to do using the generalized product rule. Okay, let's move on to the sum rule. I'll go ahead and read this, but then we'll talk about it so that it'll make a little bit more sense. The sum rule says, consider n sets a sub 1 up to a sub n. If the sets are mutually disjoint. Now, what does mutually disjoint mean? It means there's no elements that are in both sets, or that are in any two sets. Okay, so it says a sub I intersect a sub j is the empty set as long as I and j aren't the same. So it's just saying the sets do not overlap. Okay, they're all mutually disjoint. So if we have these mutually disjoint sets, then now we're taking the union of all of the sets. So we're taking the union, but we have the lines along the outsides, which means we want to know how many elements are in the union. So the number of elements in that union would be equal to the number of elements in the first set plus the number of elements in the second set, and so on. So we just add the elements in each set, add the elements up, and we get the number of elements in the union. And looking at this example down here, you see that it's a very simple concept, right? We've got three sets, a sub 1 up through a sub 3. We've got, if these dots represent the elements in the set, then, and they're not overlapping at all, then if I say how many elements are in the union of A1, A2, and A3, we would just count the number of elements in A1, count the number of elements in A2 and A3, and add them all up. So we've got 4 elements in A1, 2 elements in A2, and 3 elements in A3. So using the sum rule, we would say that the number of elements in the union is just the sum of the individual numbers. So we would have 4 plus 2 plus 3. That would equal 9. And remember, this is only true if the sets are disjoint, right? Because if I had one of these sets overlapping another set so that there's an element that actually appears in both, we'd see that, yeah, this wouldn't work because I'd be counting that element twice. And, and that would not be giving me the right answer. So now how are we going to use the sum rule in the case of these types of questions that I've been asking? Well, let's look at this question. How many different serial numbers, using digits 0 through 9, of length 3, 4, or 5 are possible? So we used that generalized product rule to answer questions like this if we were given a certain length, like of length 3, we could answer that, or of length 4, or of 5. But what about if we say, well, we want the number of, if we say that it could be either length 3, 4, or 5, how many different serial numbers would we have? Well, since, we can look at the sets of serial numbers and realize that there's no serial numbers that have a length of both 3 and 4, or 4 and 5, we would say that these sets, the set of serial numbers with a length of 3 compared to the set of serial numbers with length 4 and then with length 5, they are disjoint sets. There's no serial number that has 2 different lengths. So these sets are disjoint, so we could use the sum rule. So we could say, well, let's first of all find out how many serial numbers of length 3 we have using the generalized product rule. Then we'll find out the number of ones for length 4 and number of length 5, and then we'll add them together because that's what the sum rule says we can do. So then the number altogether of numbers length 3, 4, or 5 would just be the number of serial numbers of length 3 plus the number for length 4 and the number for length 5. So let's go ahead and do that. So for serial numbers of length 3, there's 3 slots, and we have the option of 0 up through 9 for each of those slots. So that's 10 options. So 10 times 10 times 10, 10 to the third. I'll leave it like that. We would then write it as 1000, but I'm just going to leave it like this here for now. Serial numbers of length 4, there's 4 different choices, each having 10 possibilities, so it would be 10 to the fourth. And for serial numbers of length 5, there's 5 choices, so 10 to the fifth. So the number of serial numbers of length 3, 4, or 5 would equal the sum of all of this. So it would be 10 to the third plus 10 to the fourth plus 10 to the fifth. And then we could go ahead and, find that out, and that would be pretty easy to do. I'm not sure if I have it on the slide here, but we would go ahead and find the answer there. Okay, so that takes care of the first 2 sections. Now we're on to the third section, and that section involves what are called permutations. So what is a permutation? Well, it's really a fairly simple concept in that it's just an arrangement of R objects in a specific order. So for instance, let's say I take 5 people, these people being the objects, and I have them line up in a certain order. That would be a permutation. If I change the order, I'd be coming up with a different permutation. So it's just really the order of a certain number of objects, and the order does matter. Now if we were thinking of just a set in general, like I take 5 people and I say they're all on a committee, and they're just, that's just a set of people, there's no order in there. But if I say, no, I want them lined up in a certain way, or that kind of thing, that's when we would call it a permutation. So a permutation is an arrangement of R objects in a specific order. Now here's how the book describes this, and we'll talk about how it means exactly what I just said, the same thing. It says an R permutation is and sometimes they call it an R permutation as opposed to just a plain permutation. An R permutation is a sequence of R items with no repetitions, all taken from the same set of size n. So they're saying, we've still got R items, or we could call them R objects, and they say with no repetitions. Well, why are they saying that? Well, the idea would be, some of the things we've done in the past here, we were saying, well, we can use numbers and we can repeat the numbers. We can have a serial number with a 1 in it, and then for the first slot, and then another 1 in it later, so those would be repetitions. But if you're really thinking about this, is you're taking physical objects and arranging them in order, you realize, yeah, there's going to be no repetitions, right? Because if I have 5 people and I put them in a certain order, one person's not going to be in line first and then at the end also. There's only one place, okay? So if you think about it as physical objects, you realize there's no way there's repetitions. You were just taking a certain number of objects and putting them in a certain order. And this goes on to say that the objects are taken from a set of size n. So we're going to usually use n for the number that represents how many objects we're actually going to be pulling out. I'm sorry, n is the actual number of objects that are possible. But R then will be the number of objects that we pull out. Okay, so an R permutation is a sequence of R items with no repetitions, all taken from the same set of size n. Now the book denotes a permutation, an R permutation, like this, with a capital P and then in parentheses two numbers. The first number is going to be the number of objects that we can choose from, and then second number is how many actual objects are chosen to put in a certain order. So N and R. So the first number is going to represent how many possibilities there are to how many objects there are all together, but second number is how many objects are actually taken out of that set to arrange. Okay, another way to denote that same permutation would be this way, and you might see it this way in a statistics class with a capital P and then some subscripts. There'll be a little number over to the left and a number over to the right. The number over to the left means how many objects are possible to choose, and then R means, how many were actually chosen out of that set to arrange. And then the P, again, all of this whole thing, the P with the N and the R, that represents the number of ways that it could be arranged, that those objects can be arranged. Okay, now, since the book sometimes talks about an R permutation, then we need to talk about in terms of what the book would call a plain permutation without the parameter R. Again, that first definition that I gave way at the top, that's all you really need to know. We're taking objects and arranging them in certain orders. But the way the book describes it says a permutation without the parameter R is a sequence that contains each element of a finite set exactly once, again meaning we're taking physical objects out and so they can't be repeated. But then they go on to say this, because we're saying we're making the distinction, we're not involving R. We don't say, we don't call it an R permutation, we're just calling it a permutation. And that's because we're going to take all of the elements from the set and arrange them. So it says this is a sequence of n items taken from a set of size n. So that second number is the same number as the first, because we're not just going to pick some of the objects out and arrange them, but we're going to take all of the objects that are possible and arrange them. So that would be this permutation of n things taken n at a time. That's a lot of times how we read this. The first number would be how many things we have to choose from, and then the second number would be how many we're actually choosing. So n things taken n at a time. Same number there. So if they don't mention the R, then you know we're taking all of the objects and arranging them. Now we have a formula. And remember this notation, the capital P and then the N comma R, that represents the number of ways that these objects can be ordered. So the arrangement of n objects in a specific order using R objects at a time is called a permutation of n objects taken R object at a time, and it's written like this, and here's the formula. So that number is actually equal to what we get when we plug in these n and the R into this formula. So n factorial on the top and n minus factorial on the bottom. So let's just now look at some examples. This says, how many different lineups of 6 people can I create using 12 students in a classroom? So I have 12 students to choose from, so 12 would be my n, right? But I'm only picking 6. So I would need to find the number of permutations of 12 students taken 6 at a time, right? So it would be, I'll use this notation with the capital P and then the 12, little 12 and the 6, meaning I've got 12 students to choose from, but I'm only choosing 6 and I'm lining them up. How many different ways can we do that? Well, we'll use the formula. So 12 goes in for n and 6 goes in for r. So we have 12 factorial on the top, 12 minus 6 factorial on the bottom. Now, at this point, you might just get your calculator out and start finding the numbers, 12 factorial and then 6 factorial. and see what you get. And if you have a scientific calculator that's got a factorial button, then that wouldn't be that hard. But when we're working with factorials like this, like we are in these problems, it we can simplify things and not have to rely so much on our calculator. So watch this. Let's think about what 12 factorial is. 12 factorial is 12 times 11 times 10 times 9 times 8 times 7 times 6 all the way down to times 1, right? But I'm going to stop at 6 and just say 6 factorial. And that would be the same thing, right? That would still mean I'm going from 6 all the way down to 1. But the reason I stopped there is because I have a 6 factorial on the bottom. And so if I write it this way, I see that I can cancel out the 6 factorials. And so I end up with just the 12 times 11 times 10 times 9 times 8 times 7. So you could put that in your calculator and you would get this answer. Now, as I said, if you had a scientific calculator with the factorial button, I suppose it's easier to just do the 12 factorial and then say divide 6 factorial as opposed to typing in a 12 times an 11 times a 10, that kind of thing. So I guess, if you do have some kind of setup where you can just get the answer right away, I guess there's no reason why you can't. But in my problems, I'm always going to go through this little step here where I kind of simplify things as much as possible, mostly so that we can see that it can come down to a calculation that doesn't involve factorials and is, fairly simple. So this would be the number of ways that I could line up 6 people out of a possible 12. And that's crazy, right? To think that there would be 665,280 different ways. But I can choose different groups of 6, and then each group of 6 that I have, I can arrange them in a bunch of different orders. And so this is what it comes up with. This is the number of ways. Okay, here's another question. In how many different ways can we arrange 2 pictures on this wall if we have 4 pictures to choose from? So we've got the 4 pictures to choose from, and we're going to put 1 picture on the left and 1 picture on the right. So we would think, well, what is N and what is R? N is how many objects we have to choose from, and so that would be the 4. And then 2 means how many objects we're actually going to choose, and we're only going to choose 2 pictures to put on the wall. So we'll have R being 2. So we're taking a permutation of 4 objects taken 2 at a time. And that would be 4 factorial over 4 minus 2 factorial. When the numbers are small, this is where the simplifying can really pay off, because here we've got 4 factorial over 2 factorial. If I write the 4 factorial as 4 times 3 times 2 and then stop there and just write factorial after the 2, then I see that I can cancel my 2 factorials, and so I end up with just a 4 times a 3, which is 12. So there's 12 different ways to arrange those pictures on the wall. Here's another example that we might not see as a permutation at first, but then you'll realize that's what it comes down to. A contest is being given in which there will be a first prize, a second prize, and a third prize. There are 34 entries. How many different winner lineups are possible? So, I guess you could say, imagine each of those entries as maybe a person, even though, in reality, maybe somebody had more than 1 entry. But let's just to make it simple, say that this just represents 34 people. You could say that, imagine just a lineup up at the front where there's a podium for first place and a podium for second place and third. So you could see, yeah, I'm taking these 34 people and I'm arranging only 3 of them, and I've got them in a certain order. And the order would matter because it makes a big difference whether you're third prize or first prize, right? So you can kind of see how it would be considered a permutation even though we're really, not physically arranging the objects. We'd be handing out prizes, but it, could correlate to actually physically arranging these people. Okay, so how many different winner lineups are possible? So it would be a permutation of 34 things taken 3 at a time, because there's 34 possibilities and we're just picking 3 of them, and we care about the arrangement. So it would be the 34 factorial, because 34 is n, and then underneath it'd be the 34 minus 3 factorial, which would be a 31 factorial. Then again, we could write the 34 this way, going down to 31 factorial, and then cancel the 34 going down to 31 factorial, and then canceling the 31 factorials, and we would end up just with a 34 times 33 times 30. And I advanced the slide a little too quickly before I said what the answer was, so you saw that the answer there on that last slide ended up being a little over 35,000. Okay, here's another problem. How many different ways can a 26-member sorority elect a president, vice president, secretary, and treasurer? So again, you could look at it as, there's certain seats in it, up at the front table where the president sits one place, vice president in another, and so on. If you could consider that, it could be a physical arrangement, but in reality, it's not necessarily going to be that. They're not going to necessarily be sitting there, but you can see that we would still work the problem like this as a permutation. So we would ask ourselves what's N and what's R. So there's 26 members possible, but there's only four offices. So we would say we're taking 26 things 4 at a time. We want the number of permutations. So we could say it's 26 factorial over 22 factorial, because 22 is the n minus r, and then we'll do some canceling there, and we get this 388,800. Now we could make things a little bit more complicated, and we'll call this type of problem gluing objects together in a permutation. So let's read this problem and you'll see what we mean. A wedding party consisting of a bride, a groom, 2 bridesmaids, and 2 groomsmen line up for a photo. How many ways are there for the wedding party to line up so that the bride is next to the groom? Now, obviously, it wouldn't make sense to have a wedding photo where the bride and the groom aren't standing next to each other, right? So the idea is that, we might have, the bride and groom all the way over to the left, and then the bridesmaids and groomsmen would be somehow arranged over on the right. Or we could have the bride and groom right in the middle. So there's all these possibilities, but the bride has to stay next to the groom. Although we've got to understand that maybe if we take a picture where the bride is to the left of the groom, then it would be considered a different lineup if we kept everybody in their same slot except just changed the groom and the bride's positions. That would be considered a different lineup, right? So, we got to figure out how to do this. And so the problem, it's different from the others since we have to make sure the bride and the groom sit together. So here's our strategy. Here's what we can do. We can think about gluing the bride and groom together and considering them one object. So originally there were 6 people, because the 2 bridesmaids, 2 groomsmen, and then the bride and groom. But we're going to count the bride and groom as 1. So really, let's say there's only 5 objects. So then we're going to find, take all 5 of those objects and arrange them, in all the different ways, and we would be finding permutation of 5 objects taken 5 at a time. And but again, that is only going to represent half of the number of lineups, because for every way that's in that if we consider the bride and groom being together, every lineup like that, we could swap the bride and the groom and reverse them. And so really what we need to find is that permutation, 5 things taken 5 at a time, but then multiply that number by 2, because as many times as we have 5 things taken 5 at a time, we could have a whole another set of that same number, but with the bride and groom switched. So we would take 2 times the 5 things taken 5 at a time. Now, we could go ahead and find the permutations of 5 things taken 5 at a time. But I will say this, that a lot of times in your book, when you're doing participation problems or even challenge problems, they want you to answer just in terms of something like P and the 5, 5 in there. So you would actually, if you were answering just P 5, 5, you would type in capital P and then parentheses 5, 5. But for this one, then you'd have to put somehow designate it 2 times P of 5 times 5. And the book will tell you how to designate those kinds of things, but I'm not positive if I'm even going to, on this slide, find the answer. So that's why I want to talk about it before I hit the next click, so that in case this is the last on the slide, I won't be, I'll have said everything I wanted to say. Okay, so anyway, this is how we would find it, and maybe this is all we would have to put in, something like 2 and then a star and then the P5, 5 for a certain, certain answer. But, maybe I would ask, what is the actual answer? Give me a number, and then you would need to find this. So you'd have put, 5 in for N, 5 in for R, and then find P 5, 5, and then take 2 times it to get the answer. Okay, so we've talked about everything we need to for these first 3 sections. So I've given you some additional exercises to do. You're going to have participation problems and some challenge problems. So you'll have, I think, plenty of practice, but it never hurts. Practice it never hurts to do more and more of it. It can only help. So I've opened up some of the additional exercises in the first 2 sections so that you can get some extra practice. So go ahead and take a look at those if you want to and see if you can get those. In addition to doing these and also doing what is assigned to you for the participation and challenge exercises, there's another way that you can test yourself too that I want to mention, and that is by doing all of these problems that we've just talked about here in this lesson, doing those over. So you can pull down the notes, download the notes from Canvas, and maybe cover up the solution that we went over together and just look at the problem itself, try to solve it. And if you have problems, you can always look at the answer and even listen to the video where I describe it in detail. So that's even a better way to go. If you're still a little unsure of how to do the problems, try to work through the ones I've talked through first, and then you can go to these other ones too. But hopefully you'll get plenty of practice, and I think you'll probably do okay. But let me know if you do have any questions, and I'd be glad to help.